story of the universe did not begin with the Big Bang. That single sentence changes everything. It breaks the most common belief about where reality started. It opens a door to a much deeper mystery, one that science is still trying to understand. The Big Bang is often called the birth of space and time, the moment when everything came into existence. But that idea is not as solid as it sounds. In fact, some of the greatest minds in physics, including Richard Feynman, showed that the Big Bang is not a true beginning. It is a boundary. It is the edge of what our current equations can describe. And beyond that edge, there is a question that remains wide open. In this video, you will learn why the Big Bang is not the first chapter of existence. You will learn what it actually represents, what it explains, and what it does not. You will see how modern physics quietly admits that something came before it, even if we do not yet know what that something was. You will discover how scientists separate observation from assumption, and how Feynman's way of thinking forces us to be honest about what we know and what we only guess. By the end of this video, the universe will feel less like a story that started once and more like a story that may never have had a simple beginning at all. The Big Bang is often described as a massive explosion that created everything. That is simple. It is easy to remember. It is powerful, but it is also misleading. The Big Bang theory does not describe a creation event. It describes expansion. It describes how space stretched, how energy cooled, how matter formed from extreme heat and density. It tells us how the universe evolved after a certain moment. It does not tell us why that moment existed in the first place. It does not tell us where space came from, why time started ticking, or what made the laws of physics appear. Those are deeper questions, and they remain unanswered. Richard Feynman was famous for cutting through confusion. He believed that the worst mistake in science was pretending to understand something when you did not. He taught that honesty was more important than comfort. When physics reaches a point where equations stop working, he would not accept poetic answers. He would say, "We do not know yet." And when it comes to the origin of the universe, that is exactly where we stand. The Big Bang marks the limit of our understanding. It is not the start of everything. It is the start of our reliable descriptions. This video is not about destroying science. It is about strengthening it. It is about showing how real science grows by admitting its limits. You will see why scientists say the Big Bang was not the beginning, even while they continue to trust the evidence that supports it. You will see how space, time, and energy might have existed in some form before the hot expansion that created the universe we observe today. And you will see why this idea does not weaken the Big Bang theory, but actually makes it more powerful and more honest. There's something quietly dramatic about this truth. For decades, textbooks simplified the story. They taught that time began at the Big Bang, that space began at the Big Bang, that nothing existed before it, that physics has moved forward. The equations of general relativity show that when you trace the universe backward, density increases, temperature increases, and space shrinks. Eventually, the math reaches a point where it stops making sense. That point is called a singularity. But a singularity does not mean a real physical event. It means the theory is incomplete. It means the tools fail. It means we have reached the edge of what we can calculate, not the edge of what exists. Feynman warned against a confusing mathematical breakdown with physical reality. When a theory breaks, it does not mean nature breaks. It means our description is missing something. And that is exactly what happens at the Big Bang. The laws we use collapse under extreme conditions. Quantum effects dominate. Gravity becomes uncontrollable. Space and time behave in ways we do not yet know how to describe. So calling that point the beginning is more a statement about our ignorance than about the universe itself. In this video, you will learn how scientists discovered this problem. You will learn why inflation theory suggests that space existed before the hot Big Bang phase. You will learn why some models describe the universe as eternal without a first moment. You will learn how quantum physics hints that time itself might not behave the way we think at the deepest level. And you will learn how all of this fits naturally with Feynman's demand for intellectual honesty.
There is a quiet tension at the heart of cosmology. On one side, we have incredible evidence that the universe expanded from a hot, dense state. On the other side, we admit that this does not explain ultimate origins. The cosmic microwave background radiation shows us a glowing afterimage of the early universe. The motion of galaxies shows us that space is still expanding. The abundance of light elements confirms that the universe was once extremely hot. All of this is strong. All of this is real. But none of it tells us why the universe exists at all. None of it tells us whether something came before. It only tells us how things evolved after a certain point.
That is where Feynman's thinking becomes powerful. He taught that science is not about giving final answers, it is about building better questions. When people say the Big Bang was the beginning, it sounds complete. It feels finished. It feels comforting. But when scientists say the Big Bang was not the beginning, the universe suddenly becomes much larger in meaning. It becomes open-ended. It becomes a mystery that still invites discovery. This video will take you into that mystery. It will show you how cosmology quietly shifted from talking about beginnings to talking about boundaries. It will show you how the phrase "before the Big Bang" is no longer forbidden in serious physics. It will show you how modern theories allow space and time to exist in forms we barely understand. And it will show you why admitting uncertainty is not weakness but strength. It will also learn why the Big Bang remains one of the most successful scientific models ever created, even while it does not explain ultimate origins. It explains structure, it explains evolution, it explains change, it explains why the universe looks the way it does today, but it does not explain existence itself. And that difference matters more than most people realize. By the end of this video, the Big Bang will no longer feel like a final answer. It will feel like a doorway into deeper physics, a doorway into deeper questions, a doorway into a universe that might not be limited by a starting point in time. You will see why Feynman would be excited by this, not frustrated by it. He believed that uncertainty was the engine of discovery, and nowhere is uncertainty more powerful than at the origin of everything. Stay with this video until the end, because the idea that the universe did not begin with the Big Bang is not just a technical detail. It changes how we think about time, existence, and reality itself. It reshapes the story we tell about where we come from. It transforms the universe from a finished tale into an unfinished investigation. And that is far more thrilling than a simple beginning could ever be.
If you enjoy content that explores the deepest ideas in science with clarity, honesty, and curiosity, then you are in the right place. Welcome to our channel, where we question what seems settled and explore what remains unknown. Subscribe now and join us as we continue uncovering the hidden layers of reality, one mystery at a time.
Most people grow up hearing the same story. The universe began with the Big Bang. Time started. Space started. Everything appeared at once from nothing. It is taught as a clean and simple moment, like the opening scene of a movie. 1 second there was nothing, and the next second there was everything. This idea is powerful, so it stays in the mind. It feels complete. It feels final. It feels like the answer to the biggest question. The Big Bang is often described as a massive explosion in empty space, a sudden blast that threw matter and energy outward in all directions. Galaxies flying away from a central point, light bursting into existence, time beginning its flow, space unfolding like a stretched fabric. This image is dramatic, and it is easy to understand. That is why it appears in books, documentaries, and classrooms. It turns the origin of the universe into a single event that can be imagined in a simple way. People are taught that before the Big Bang there was no time, no space, no matter, no energy, no laws of physics, just nothing. And then suddenly everything. This story makes the universe feel like something that was created in one instant, like a switch being flipped. It suggests that science has already solved the question of origins. It gives the impression that we know where existence began and how it started. But this picture hides many complications. It mixes scientific language with everyday ideas that do not really fit. An explosion needs space to explode into. It needs a center. It needs something surrounding it. The Big Bang does not work like that. It was not an explosion in space. It was an expansion of space itself. There was no outside. There was no central point. Every place was once compressed together. Still, the simple version remains popular because it feels satisfying. It gives a clear beginning. It gives a moment you can point to and say, that is where everything started. It turns the universe into a story with a sharp opening line. But physics is rarely that neat. The deeper scientists looked into the equations, the less comfortable the simple picture became. The more they realized that the Big Bang, as commonly described, was not really a beginning in the way people imagine it. The Big Bang is not a story about creation. It is a story about change. It is a model that explains how the universe evolved from an extremely hot and dense state into the vast and cooler universe we see today. It describes motion, temperature, and structure. It shows how simple beginnings turned into complexity over time. It does not explain why the universe exists, but it explains how it transformed. One of the strongest signs comes from the way galaxies move. When scientists look at distant galaxies, they see that almost all of them are moving away from us. The farther a galaxy is, the faster it appears to be receding. This is not because we are at the center. It is. It is because space itself is expanding. Every region of space is stretching, carrying galaxies along with it. This pattern is exactly what the Big Bang model predicts. A universe that began in an opaque state and has been expanding ever since would show this kind of motion. Another powerful piece of evidence is the cosmic microwave background radiation. This is a faint glow that fills all of space. It is the leftover heat from the early universe when everything was packed together and extremely hot. As the universe expanded, this heat cooled and stretched into microwave wavelengths. Today it appears as a nearly uniform background signal coming from every direction. It is like a thermal echo of the universe when it was young. This radiation is not random. Its tiny variations show patterns that match precise predictions made by the Big Bang model. Those patterns reveal how matter was distributed long before stars and galaxies formed. They show that the early universe was smooth, hot, and dense, with slight irregularities that later grew into cosmic structures. This is not guesswork. It is measured data that has been tested again and again. Together, the expanding galaxies and the background radiation tell a consistent story. The universe was once much smaller, much hotter, and much denser than it is now. Over time, it expanded and cooled, allowing particles to form, atoms to appear, and light to travel freely. The Big Bang model explains this transformation with remarkable accuracy, describing the universe's growth rather than claiming to describe its ultimate origin. When scientists push the equations of physics backward in time, they reach a strange limit. The density of the universe rises, the temperature climbs, space shrinks, gravity grows stronger. Eventually, the numbers explode to infinity. This point is called a singularity. It sounds like a real physical moment, but it is not something we can actually describe. It is where our mathematics stops working. It is where our current theories lose their power. A singularity does not mean that nature becomes infinite or broken. It means our tools are no longer good enough. The equations we use were never meant to handle conditions that extreme. They were built to describe stars, galaxies, and large-scale space, not the deepest structure of reality. When they fail, they signal that something deeper is missing from our understanding. Calling this point the beginning of everything is a misunderstanding. It comes from taking the equations and running them backward until they collapse. But when a map ends, it does not mean the world ends. It only means the map is incomplete. In the same way, the singularity marks the edge of what our physics can describe, not the edge of existence itself. At that scale, quantum effects become dominant. Space and time no longer behave smoothly. They may fluctuate. They may lose their familiar meaning. Gravity and quantum mechanics, the two pillars of modern physics, stop working together. We do not yet have a theory that unites them under such extreme conditions. Without that theory, any claim about an absolute beginning becomes speculation, not science. So the Big Bang singularity is not a real moment we can point to and understand. It is a warning sign in our equations. It tells us that our models are incomplete. It shows us where new physics must exist. The idea of a beginning comes from mistaking a mathematical breakdown for a physical event. As physics moved forward, scientists began to see signs that the hot Big Bang was not the first event in the story. It was not the start of everything, but the start of what we can directly observe. One of the strongest ideas behind this comes from the theory of cosmic inflation. Inflation suggests that space was already expanding before the universe became hot and dense. In that earlier phase, space itself grew at an extreme rate, faster than anything we see today. This expansion set the stage for what later became the hot Big Bang. In this view, the Big Bang is not the moment when space appeared. It is the moment when space changed its behavior. Before it, expansion was driven by a powerful field that stretched the universe rapidly and smoothly. After it, the energy of that field transformed into heat, particles, and radiation. The universe became filled with matter and light. The hot, glowing phase began. That transition is what we call the Big Bang. This changes how the timeline of the universe is understood. The Big Bang marks the start of our observable history, not the start of time itself. It is the point where the universe became transparent enough for light to travel. It is the moment from which we can gather evidence. Anything before it is hidden from direct observation, not because it did not exist, but because its signals were erased by later expansion. Modern physics treats this seriously. It does not assume that existence started at the Big Bang. It treats it as a boundary of information. The universe before that boundary may have had structure, motion, and even its own form of time. The difference is that we do not yet know how to measure it. This is why scientists speak carefully. They say the Big Bang begins our known story, not the full story. It is like opening a book in the middle of a chapter. The pages before still exist, even if we cannot read them yet. The current expansion of the universe becomes one phase in a much longer process, one chapter in a much larger sequence that may stretch far beyond what we can currently see or describe. When we push physics to its extreme limits, it begins to lose clarity. Our best theories work beautifully for most of the universe. They describe planets, stars, galaxies, and even black holes with incredible accuracy. But when energy becomes too high and distances become too small, those same theories stop cooperating. The equations that guide our understanding begin to contradict each other. Gravity becomes too strong. Quantum effects become too wild. The language of physics itself starts to blur. General relativity explains how space and time bend under gravity. Quantum mechanics explains how particles behave at tiny scales. Both are powerful. Both are tested. But they do not fit together in extreme conditions. At the earliest moments of the universe, gravity and quantum effects would have acted at the same time with equal strength. We do not yet have a theory that can handle both at once. Because of that, we cannot describe what happened before the hot Big Bang with confidence. We are missing the mathematics. We are missing the structure. We are missing the rules. This is not a failure of science. It is an honest boundary. It tells us where knowledge ends and questions begin. Any description of before the Big Bang today is incomplete. Some ideas are promising. Some are elegant. Some are bold. But none are proven. Without experimental evidence, they remain possibilities, not facts. Richard Feynman respected this kind of uncertainty. He believed that pretending to know was more dangerous than admitting ignorance. He warned against building stories that sounded convincing but lacked real proof. For him, a theory had only one job. It had to match reality, not imagination, not beauty, not emotional comfort, only reality. So when scientists say they do not know what came before the Big Bang, they are not being weak, they are being precise. They are protecting science from turning into philosophy dressed as physics. Feynman would remind us that mystery is not something to hide, it is something to respect. It is the signal that discovery is still possible. Because the idea of a single beginning creates so many problems. Physicists have explored other ways the universe might exist without a first moment. One of these ideas is the cyclic model. In this view, the universe does not start once and end once. It expands, slows down, contracts, and then begins again. Each cycle leads to another. There is no original creation point, only an endless rhythm of change. Expansion becomes one phase, contraction becomes another. Time stretches backward and forward without a clear starting line. In a cyclic universe, the Big Bang is not a birth. It is a transition. It marks the shift from a collapsing phase to an expanding phase. The universe does not appear from nothing. It reshapes itself. Matter and energy pass through different states, governed by deeper laws that remain hidden from direct observation. This removes the need for a first moment because the universe is always in motion, always evolving. Another powerful idea is eternal inflation. According to this theory, space itself is constantly expanding in different regions. Some areas slow down and form universes like ours. Others continue expanding forever. Each universe becomes a bubble inside a much larger structure. Our Big Bang would be the birth of one bubble, not the birth of everything. In this picture, universes are not rare events. They are natural outcomes of an ongoing cosmic process. Eternal inflation changes the scale of reality. The universe becomes far larger than what we can observe. What we call the universe becomes only one small part of a much greater system that has no clear beginning or end. Quantum theories add another layer. At the smallest scales, time may not behave in a straight line. Space and time may emerge from deeper quantum processes. Some models suggest the universe did not begin from a singular point at all. Instead, it passed through a quantum phase where the idea of a beginning loses its meaning. These ideas challenge the need for a single starting moment. They replace a sharp origin with continuous transformation, endless generation, or timeless structure, shifting the question from when everything began to how reality keeps unfolding. What we can say with confidence is that the hot Big Bang marked the beginning of the universe as we know it. It was the moment when the universe became hot, dense, and filled with energy and particles. It was the point where space was small enough and temperatures were high enough for the basic building blocks of matter to form. It was the start of structure, motion, and change,
that we can trace using evidence. It was the beginning of a story we can measure.
Before that moment, the universe may still have existed, but not in a form we can directly describe. The hot Big Bang marks the moment when the universe became transparent to light. Before that, energy and particles were locked together in a dense fog. Light could not travel freely. Information was trapped. When the universe cooled enough, light escaped. That is the earliest signal we can observe today. That is why our history begins there. So when scientists say the Big Bang started the universe, they often mean it started the observable universe. It started the part of reality we can test, measure, and confirm. It started the timeline that leaves traces in radiation, motion, and structure. It is the earliest chapter that left behind evidence. But existence itself may not be limited to that moment. Space may have existed in another form. Time may have flowed in another way. Energy may have been stored in different fields or states. The laws that shaped the hot Big Bang may have been operating long before it. The difference is that we do not yet know how to read that earlier chapter.
This shifts the meaning of start. The hot Big Bang becomes a starting point of clarity, not creation. It is where the universe became understandable through physics. It is where patterns began to leave fingerprints we could later detect. It is where the universe began telling its story in a language we could eventually learn to read.
The beginning, then, is not of existence itself, but of visibility, structure, and history that science can trace. It is the beginning of evidence, not necessarily the beginning of reality. The Big Bang gives us a powerful explanation for how the universe developed after a certain moment, not why existence began in the first place. It shows how energy cooled into particles, how particles formed atoms, how atoms gathered into stars, and how stars built galaxies. It explains motion, structure, and change. It gives us a timeline of transformation, but it does not give us a reason for existence. It does not explain why there is something rather than nothing. This is an important distinction. Many people treat the Big Bang as an answer to the deepest question. In reality, it is an answer to a different question. It explains how the universe evolved once it was already in motion. It describes the growth of complexity from simple beginnings. It shows how order emerged from extreme heat and density. But it stops when we ask what caused that state to exist at all. Science works by following evidence. It builds models that match observation. When those models reach their limits, science does not force an answer. It marks the boundary and keeps searching. The Big Bang sits at one of those boundaries. It is not a wall that ends inquiry. It is a signpost that points toward deeper layers of reality that we have not yet learned to describe. Each time physics reaches a limit, new ideas appear, new theories form, new experiments are designed, questions become sharper. The unknown becomes a guide rather than an obstacle. The origin of the universe remains one of those open questions, not because science failed, but because the universe is deeper than our current tools. This is how scientific understanding grows. First, we explain patterns. Then we explain causes. Then we discover that causes themselves need explanation. The Big Bang explains evolution, not existence. It gives structure to time, but not to time's origin. It tells us how the universe changes, but not why change exists at all. So science continues forward, not with certainty, but with curiosity. Each answer reveals new questions. Each discovery opens new mystery. The universe becomes less like a solved problem and more like an ongoing conversation between reality and human understanding. The universe does not become smaller as we learn more about it. It becomes larger in meaning. Every time science pushes forward, the horizon moves back. What once looked like an ending turns into a beginning of deeper questions. What once felt complete opens into something far more complex. The idea that the universe may stretch further in time than we can measure changes how existence itself feels. Reality stops being a single event and starts becoming an endless process. If the Big Bang is not the true beginning, then time may not be a straight line with a sharp starting point. It may be a vast landscape with layers we have not yet reached. The universe may carry a history that does not fit inside human intuition. Its story could extend beyond any calendar, beyond any equation we currently hold, beyond any simple definition of origin. This does not make the universe colder or more distant. It makes it richer. It means existence is not fragile. It is not balanced on a single moment. It is supported by deeper structures that remain hidden but real. The universe becomes something that did not merely appear, but something that continues, transforms, and unfolds in ways that challenge every limit of thought. There is something powerful in knowing that the greatest questions are still open. It means discovery is not over. It means understanding is still growing. It means reality is larger than our current imagination. The unknown is not empty. It is full of possibility. When we accept that the universe may be older than time as we define it, wider than space, as we measure it, and deeper than logic as we apply it, science becomes more than explanation. It becomes exploration. It becomes a journey into ideas that reshape how existence itself is understood. The universe stops being a finished answer and becomes an invitation to question, an invitation to learn, an invitation to accept that reality is not limited by human language or human models. It is larger than any single story. That realization carries a quiet excitement. It means that even the greatest discoveries are not endings. They are openings. They are signs that the universe is still revealing itself, layer by layer, mystery by mystery, stretching far beyond what we once believed was possible. The Big Bang was never meant to be the final answer. It was meant to be a doorway into deeper questions, deeper physics, and a deeper understanding of reality itself. It shows us how the universe evolved, not why it exists. And that difference matters. When we accept that the universe may not have a simple beginning, we stop looking for a single moment and start looking for a greater story. A story that may stretch beyond time, beyond space, and beyond our current imagination. That is not confusing. That is powerful. It means discovery is still alive. It means the universe still has secrets waiting to be uncovered. If this video changed the way you think about the origin of everything, then take a moment to support the channel. Like this video so more people can discover it. Subscribe to our channel for more deep, honest explorations of science and reality. And join us as we continue searching for the truths that lie beyond the limits of what we think we know.